What if you have already died? Not once, not twice, but thousands of times. Car crashes you do not remember, diseases that should have killed you, a million close calls that went the other way. The physics is real, the math is published. And the man who discovered it drank himself to death before the world believed him. Tonight, we investigate the multiverse, quantum immortality, and the terrifying possibility that you cannot die, no matter how much you might want to. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. What if death is not an ending but a fork in the road? What if every time your heart stops, every time the car swerves, every time the diagnosis comes back terminal, there is another version of you somewhere who survives? Not in heaven, not in some spiritual afterlife, but in a parallel universe running alongside this one, separated by nothing more than the thickness of a quantum measurement. The theory is real, the physics is published, and the implications are so disturbing that the man who discovered it drank himself to death before the world took him seriously. Tonight we go deep into multiverse theory, quantum immortality, and the terrifying possibility that you have already died countless times and simply do not remember. That you reading these words right now might be the survivor of 1,000 near misses, 1,000 car crashes, 1,000 failed surgeries, and you would never know because the dead versions cannot report back. Chapter 1, The Day You Died and Kept Living. March 15, 1954, Princeton, New Jersey. A graduate student named Hugh Everett III sits in his apartment with a glass of cherry, staring at equations that will not balance. He is 23 years old, brilliant, and deeply troubled by a problem that has haunted physics for 3 decades. The problem is simple to state and impossible to solve. When you look at something very small, an electron, a photon, a single atom, it changes. Before you look, the particle exists in multiple states at the same time. After you look, it snaps into one clear state. The math is clear. The experiments confirm it. But what happens to all the other possibilities? Where do they go? The standard answer, called the Copenhagen interpretation, says they simply vanish. The act of observation collapses the wave function. All possibilities except one stop existing. This is what Niels Bohr taught. This is what Werner Heisenberg defended. This is what every physics student learns in their first quantum mechanics course. And Hugh Everett thinks it is nonsense. He takes another sip of cherry. Outside, the March wind rattles the windows of his cramped apartment. His wife is pregnant with their first child. He should be thinking about the future, about jobs, about money. Instead, he is thinking about the nature of reality itself. Because if the Copenhagen interpretation is correct, then consciousness has a special role in physics. The observer matters. The universe cares whether you are watching, and that seems impossible, unscientific, almost religious. There has to be another answer. Everett begins to write. His pen moves across the yellow legal pad in quick, certain strokes. What if the wave function never collapses at all? What if every possibility, every possible outcome actually happens? Not metaphorically, not philosophically, but physically, in branching parallel universes that split off from each other at every quantum measurement. The observer does not collapse the wave function. The observer becomes entangled with it, and both outcomes occur, each in their own separate branch of reality. It sounds like science fiction. It sounds insane. But Everett works through the mathematics and finds that it is completely consistent with quantum mechanics. More than consistent. It actually solves several long-standing paradoxes. The measurement problem vanishes. The role of the observer becomes ordinary. The equations finally make sense. He calls it the relative state formulation. Later, others will call it the many worlds interpretation. But on that night in 1954, Hugh Everett has no idea that he has just proposed one of the most radical ideas in the history of science. He has no idea that his theory will be rejected, mocked, and ignored for decades. He has no idea that it will eventually be embraced by some of the greatest physicists alive. And he certainly has no idea that buried within his mathematics is a logical consequence, so disturbing that philosophers are still arguing about it 70 years later. The consequence is called quantum immortality, and it suggests that you cannot die. Let me be precise about what this means. The theory does not say you will live forever in any normal way. It does not promise eternal youth or bodily resurrection. What it suggests is far stranger. Every time you face a situation where you might die, the universe splits. In some branches, you die. In other branches, you survive. But you, your conscious experience, can only continue in the branches where you stay alive. The dead versions of you do not experience anything. They simply end. So from your own point of view, you will always find yourself in a branch where you survived, no matter how unlikely that survival might be. Think about what this means. Really think about it. You're driving on the highway. A truck crosses the median. In some branches of the multiverse, the crash kills you instantly. In others, you swerve just in time. In still others, the truck driver corrects at the last second. In a few rare branches, some strange accident saves you against all odds. Maybe the truck clips your bumper instead of crushing your door. Maybe you decided to take a different route that morning. Maybe you stopped for coffee and missed the whole thing by 30 seconds. The point is that there is some branch, however unlikely, where you survive. And that is the only branch you will ever experience. You will wake up in the hospital. You will hear the doctor say it is a miracle. You will go home and hug your family and wonder why you feel so strange. And you will never know that a trillion other versions of you are being buried this week. This is not mysticism. This is not wishful thinking. This is a logical consequence of the many worlds interpretation of quantum mechanics. And the many worlds interpretation is not fringe science. It is taken seriously by physicists at MIT, Caltech, Oxford, and Cambridge. Shah Carroll, one of the most respected physicists alive, calls it the most straightforward interpretation of the quantum equations. David Deutsch, the father of quantum computing, is a passionate advocate. Max Tegmark, the MIT cosmologist, has written extensively about quantum immortality and its implications. These are not cranks. These are serious scientists grappling with a serious problem. And the problem is this. If the mathematics of quantum mechanics is correct, and if the many worlds interpretation is the right way to understand that mathematics, then quantum immortality follows as a matter of logic. You can accept the premises and deny the conclusion, but you cannot call the conclusion unscientific. Hugh Everett understood this. In the years after he proposed his theory, he thought deeply about what it meant for mortality. He reportedly told colleagues that he did not believe in death, at least not in the usual sense. He expected to keep his experience going, always finding himself in the branch where he survived. When he died of a heart attack in 1982 at the age of 51, his body was cremated and his ashes scattered. He had left instructions that there should be no funeral, no memorial, no mourning. Perhaps he believed he was still alive somewhere in some other branch of the wave function, continuing the life he had started in this one. Or perhaps he simply could not face the alternative, because here is the dark side of quantum immortality. If the theory is correct, you will never experience death, but you will experience everything leading up to it. You will get the cancer diagnosis in some branches. You will feel the car beginning to flip. You will hear the gunshot. And then you will find yourself somehow alive against all odds again and again and again. An endless chain of near misses stretching toward infinity. You will watch everyone you love die. Because their quantum immortality is not the same as yours. They will find themselves in branches where they survive, but those branches might not include you. From your perspective, they will age and get sick and eventually disappear. And you will continue on alone, getting older, growing more frail, surviving by more and more unlikely means. A 90-year-old in a hospital bed, then a 100-year-old, then 110. Medical science advancing just fast enough to keep your consciousness flickering in some distant branch, where the nursing home did not catch fire, and the pandemic did not reach your floor, and the medication error went the other way. This is not immortality as we imagine it. This is not eternal youth or divine protection. This is the universe trapping you in an endless corridor of shrinking probability, forcing you through smaller and smaller doors until you cannot imagine how you're still alive. And yet you are, because the dead versions cannot notice their own death, because experience requires a living brain to experience it, because the quantum wave function does not care about your comfort. Hugh Everett never published his thoughts on quantum immortality. The idea appears nowhere in his original thesis or his later papers. It was left to later philosophers and physicists to pull out the implications, to name the concept, to argue about whether it was a feature of the theory or a bug. But Everett knew. You can see it in his letters, in the memories of his colleagues, in the strange fatalism that settled over him as the physics community rejected his work. He proposed a theory of reality. The theory said that you cannot die. And then he spent the rest of his life watching the world ignore him. In 1957, Everett completed his doctoral dissertation under the supervision of John Wheeler, one of the giants of 20th century physics. Wheeler was excited about the work, but careful about how it should be presented. He knew that Niels Bohr, the most respected figure in quantum mechanics, would oppose any challenge to the Copenhagen interpretation. He urged Everett to soften his language, to remove the more provocative claims, to frame the work as a mathematical reformulation rather than a basic challenge to the established view. Everett agreed. The published version of his thesis was shorter and more technical than the original. The philosophical implications were buried beneath equations. The phrase "many worlds" does not appear, but the core idea remained intact. And when Bohr finally read the paper, he rejected it completely. The response was devastating. Bohr was not just a physicist. He was the founder of the Copenhagen interpretation, the architect of quantum orthodoxy, a Nobel laureate whose authority in the field was nearly absolute. His dismissal of Everett's work was quiet but effective. No papers were published attacking the theory. No debates were held. Bohr simply declined to engage. He let it be known that he found the approach uninteresting and unnecessary. And in the small world of theoretical physics, that was enough. Everett had expected criticism. He had not expected silence. He waited for the scientific community to argue with him, to point out flaws in his reasoning, to take his work seriously enough to refute it. Instead, they looked away. The paper was published and quickly forgotten. Citations were rare. Follow-up work was almost non-existent. For 15 years, the many worlds interpretation existed as a footnote, an oddity, a road not taken. Everett left physics. He took a job with the Pentagon, working on nuclear war strategy and mathematical modeling. He made money. He raised his children. He drank heavily and smoked constantly and retreated into himself. His marriage fell apart. His relationship with his children grew distant. By all accounts, he was a deeply unhappy man, brilliant and bitter and unable to let go of the theory the world had rejected. He died in his sleep in 1982. His daughter would later describe finding his body cold and stiff in his bed, the aftermath of a massive heart attack. He was only 51 years old, and in keeping with his wishes, there was no funeral, just cremation, just ashes, just the end of a story that was not supposed to end. Except perhaps it did not end at all. Perhaps if his theory is correct, there is a branch of the wave function where Hugh Everett III woke up that morning in 1982, where the heart attack was milder or did not happen at all, where he lived to see his work proven right, to witness the revival of many worlds in the 1980s-90s, to know that some of the greatest minds in physics had come around to his view. Perhaps in some branch he is still alive, an old man now over 90, surrounded by colleagues who finally understand what he proposed all those years ago. Perhaps he reads the papers of Shaw Carroll and Max Tegmark and smiles. Perhaps H. thinks about that night in 1954, the Sherry, the equations, the moment when he first saw the branching structure of reality. Perhaps, or perhaps death is simply death. The wave function collapses into nothing, and Hugh Everett III experienced his last moment of consciousness on a morning in July 1982, never knowing that he had been right all along. The question is undecidable. The experiment cannot be run, and that is exactly the problem with quantum immortality. It is a theory that can never be tested from the outside, only from the inside, only by living through it, only by dying and not dying over and over until you find yourself ancient and confused and wondering why the universe will not let you rest. Welcome to the multiverse. The doors only open one way, and you have already walked through more of them than you could ever count. Chapter 2. The Man Who Split the Universe. To understand why quantum immortality might be real, you first have to understand the man who made it possible. Hugh Everett III was not supposed to revolutionize physics. He was supposed to be a chemical engineer. He was supposed to follow his father into practical work, steady employment, the American dream of upward mobility through technical skill. Instead, he wandered into the deepest questions about the nature of existence and came out with an answer that terrified everyone who heard it. He was born on November 11, 1930, in Washington, District of Columbia. His father, Hugh Everett II, was a military officer who rose to the rank of lieutenant colonel, working on logistics and operations research. His mother, Catherine Lucille Kennedy, was a writer and homemaker. The family was comfortable but not wealthy, stable but not warm. Hugh would later describe his childhood as lonely. He was smart. Too smart for his classmates, too smart for the rigid structure of 1940s American schooling. He read voraciously. He taught himself advanced mathematics from library books, and he learned early that the answers adults gave to difficult questions were often unsatisfying. His parents divorced when he was young, His father remained distant, a figure of authority rather than affection. His mother struggled with depression and alcoholism, patterns that would reappear with tragic force in the next generation. Hugh coped by retreating into abstraction. Numbers were clean, equations were certain. The physical world could be measured, predicted, controlled. Unlike people, unlike family, unlike the messy chaos of human relationships, he attended St. John's College High School in Washington, then the Catholic University of America for his undergraduate work. He studied chemical engineering just as his father wanted, but the pull of pure physics was irresistible. After graduating in 1953, he won a National Science Foundation Fellowship to pursue graduate work at Princeton University, one of the most prestigious physics departments in the world. It was there in the hallowed halls where Einstein had walked that Hugh Everett encountered the problem that would define his life. The problem was measurement. Here is what you need to understand about quantum mechanics. At the smallest scales, the subatomic realm of electrons and photons and quarks, the universe does not work the way you think it does. Objects do not have clear positions. They do not follow predictable paths. Instead, they exist in what physicists call superposition, a blur of possibilities, each with its own chance of being real. An electron is not a tiny ball orbiting an atom. It is a cloud of probability spread out through space, at the same time in many places at once. This is not a limitation of our knowledge. It is not that we lack the instruments to see where the electron really is. The electron truly does not have a clear position until something measures it. The math is clear on this point. The wave function, the mathematical object that describes a quantum system, spreads out through all possibilities. Only when a measurement occurs does the wave function seem to collapse into a single outcome. But what is a measurement, and why does it collapse the wave function? These questions tormented the founders of quantum mechanics in the 1920s and 30s. Niels Bohr, working in Copenhagen with Vera Heisenberg and others, developed what became the standard answer. According to the Copenhagen interpretation, the wave function is not a description of physical reality. It is a mathematical tool for calculating probabilities. When you measure a quantum system, the wave function collapses because that is what measurements do. The observer, the classical measuring apparatus, exists outside the quantum realm and forces a clear outcome onto the blurry quantum world. This sounds reasonable until you think about it. Because observers are made of atoms, measuring devices are made of atoms. If quantum mechanics applies to electrons, why does it not apply to the measuring device? Why does the wave function collapse just because a large collection of atoms arranged in the shape of a detector or a scientist happens to interact with it? Bohr never gave a satisfying answer. He spoke of the complementarity of the quantum and classical worlds, of the necessity of using classical concepts to describe experimental outcomes, of the fundamental role of observation in physics. His language was poetic, philosophical, sometimes mystical, and it convinced a generation of physicists that the question had been answered even though it had only been delayed. Hugh Everett was not convinced. He arrived at Princeton in 1953, assigned to work with John Archbold Wheeler, one of the most creative theoretical physicists of the 20th century. Wheeler was known for coining phrases like black hole and wormhole, for pushing the boundaries of general relativity, and for taking strange ideas seriously. He was exactly the right mentor for a student with a dangerous question. Everett began attending seminars on the foundations of quantum mechanics. He read the original papers by Bohr and Heisenberg, by Schrödinger and Feynman. He traced the history of the measurement problem and found it deeply unsatisfying. Everyone agreed that the wave function changed according to the Schrödinger equation, a beautiful, deterministic linear equation that never produced collapse. And everyone agreed that measurements produced collapse. But no one could explain how these two facts fit together. The mathematics said one thing, the philosophy said another, and the physics community had simply stopped asking questions. Everett asked questions. What if, he wondered, the wave function never collapses at all? What if the Schrödinger equation applies everywhere at all times, to all systems, including observers and measuring devices in the entire universe? What would the mathematics predict? The answer, when he worked it out, was startling. If the wave function never collapses, then every possible outcome of every measurement actually occurs. But they occur in different branches of the wave function, branches that cannot interact with each other, branches that are effectively separate universes. An observer measuring an electron does not cause the electron to have a clear position. The observer becomes connected with the electron, entangled with it, split into multiple versions, one for each possible outcome. And each version of the observer experiences a different result, unaware that the other versions exist. This is the many worlds interpretation in its original form. Everett did not call it that. He called it the relative state formulation, emphasizing the mathematical structure rather than the philosophical implications. But the implications were clear from the beginning. If the wave function never collapses, then the universe is constantly branching. Every quantum event, every subatomic interaction creates new branches, and we, the observers, branch along with it. Everett worked on his theory for 2 years. He filled notebooks with calculations. He discussed the ideas with Wheeler, who was fascinated but cautious. He refined the mathematics until he was certain it was consistent. And in 1956, he submitted his doctoral dissertation titled The Theory of the Universal Wave Function. The original version was long and ambitious. It laid out the mathematical framework in detail, addressed potential objections, and explained why the many worlds view was simpler and more elegant than the Copenhagen interpretation. Everett was not modest about his achievement. He believed he had solved the measurement problem, resolved the deepest paradox in physics, and provided a complete description of physical reality. He expected controversy. He expected debate. He expected the physics community to pay attention. Wheeler was worried. He knew that Bohr and his followers would react badly to any challenge to Copenhagen orthodoxy. He urged Everett to cut the dissertation down, to remove the more provocative claims, to present the work as a mathematical contribution rather than a revolutionary new world view. Everett reluctantly agreed. The published version was shorter and more technical. The philosophical discussion was reduced to a few pages. The phrase "many worlds" does not appear. It did not matter. When Bohr finally read the paper, his reaction was cold. He declined to engage with the argument. He expressed no interest in pursuing the matter. For a young physicist hoping to make a name in theoretical work, this was a death sentence. Without Bohr's approval, without serious engagement from the mainstream community, the theory would go nowhere. And for 15 years, it went nowhere. Everett defended his thesis in 1957 and received his doctorate. But by then, he had already decided to leave academic physics. The cold reception, the dismissal by Bohr, the silence of the community, all convinced him that pursuing his ideas in academia was futile. He took a job with the Weapons Systems Evaluation Group, a Pentagon think tank that assessed nuclear war strategies. It paid well. It used his mathematical skills, and it allowed him to escape the physics world that had rejected him. He did not entirely abandon his theory. Over the years, he corresponded with a few physicists who expressed interest. He revised and expanded his ideas in unpublished notes. He met occasionally with Wheeler to discuss the implications, but he never published another paper on quantum mechanics. He never returned to academic physics. He became a defense contractor, a consultant, a private researcher on classified problems. The man who split the universe disappeared into the military-industrial complex. His personal life grew darker. He married Nancy Gore in 1956, and they had 2 children, Mark and Elizabeth. But the marriage was troubled from the start. Everett drank heavily, starting early in the day and continuing into the night. He smoked 3 packs of cigarettes a day. He ate poorly, never exercised, and showed little interest in his own health. His weight ballooned. His relationship with his children was distant at best, hostile at worst. The drinking was a symptom of something deeper. Friends and colleagues described Everett as depressed, bitter, convinced that the world had wronged him. He believed his theory was correct. He believed the physics community had failed to recognize genius, and he coped with that failure through self-destruction. His daughter Elizabeth suffered from manic depression. She would later describe a childhood of neglect and emotional chaos. In 1996, years after her father's death, she died by suicide. In her note, she expressed hope that she might find herself in another branch of the wave function, reunited with her father. It was a tragic echo of the theory he had proposed. The theory that said death might not be final, the theory that had brought no comfort to his own tortured life. Hugh Everett III died on July 19, 1982. He was 51 years old. The cause was a heart attack, sudden and massive, striking him in his sleep. His body was found by his son, Mark, who would later become famous as the lead singer of the rock band Eels. The cremation was performed according to Hugh's wishes. There was no funeral. There was no memorial service. His ashes were thrown in the trash exactly as he had instructed. He did not want mourning. Perhaps he did not believe he was truly dead. In the years after his death, something strange happened. The many worlds interpretation, rejected and ignored for decades, began to attract serious attention. Physicists working on quantum computing found that the theory provided a natural framework for understanding parallel computation. Cosmologists studying the early universe found that many worlds avoided certain paradoxes in quantum cosmology. Philosophers of physics wrote papers defending Everett's approach against its critics. By the 1990s, many worlds had become a respectable position in the foundations of physics. Not dominant, certainly, not accepted by everyone, but no longer fringe, no longer laughable. Surveys of physicists and philosophers showed significant support for the interpretation, often rivaling or exceeding support for Copenhagen, the theory Hugh Everett had proposed in his cramped Princeton apartment. The theory that had been dismissed and ignored had become one of the major contenders for understanding the nature of quantum reality. Today, advocates of many worlds include some of the most prominent names in physics. David Deutsch, the pioneer of quantum computing, has argued that the parallel branches of the wave function are literally real, that quantum computers work by performing calculations across multiple universes at the same time. Shan Carroll, the Caltech physicist and popular science writer, has defended many worlds in books and lectures, calling it the simplest and most elegant interpretation of quantum mechanics. Max Tegmark, the MIT cosmologist, has written extensively about the philosophical implications, including the disturbing concept of quantum immortality. Hugh Everett did not live to see this vindication. He died believing his work had been a failure, that the physics community had rejected him unfairly, that his greatest contribution would be forgotten. He did not know that decades later his name would be cited in thousands of papers, that his interpretation would be taught in graduate courses, that his face would appear in documentaries about the nature of reality, perhaps in some branch of the wave function he knows. Perhaps there is a universe where his heart did not fail on that July morning, where he lived another 20 or 30 years, where he saw the tide turn and the world finally catch up to what he had understood in 1954. Perhaps he's alive right now, an ancient man in a distant branch, reading papers that cite his work and remembering that night in Princeton when he first saw the truth. Or perhaps death is death. Perhaps the wave function collapses after all. Perhaps Hugh Everett III experienced his final moment of consciousness in 1982 and has not experienced anything since. The question cannot be answered. The experiment cannot be run. All we have is the theory, the mathematics, the strange and beautiful idea that the universe splits at every measurement and we split along with it. An idea born in loneliness, developed in exile, vindicated in death. An idea that says the man who proposed it might still be alive somewhere in some branch we cannot reach, thinking thoughts we cannot hear. Welcome to the universe of Hugh Everett. It has more room than you ever imagined. Chapter 3. The Copenhagen Lie. Before Hugh Everett could split the universe, someone had to break it. That someone was Niels Bohr. And the breaking happened in Copenhagen, Denmark in the 1920s, when a group of brilliant physicists decided that reality was too strange to understand, and the best we could do was calculate. To appreciate how radical Everett's theory was, you need to understand what it replaced. The Copenhagen interpretation was not just a scientific theory. It was a philosophy, a worldview, almost a religion. For 60 years, it dominated quantum mechanics with an iron grip. Physicists who questioned it were ignored, ridiculed, or pushed out of the field entirely. The measurement problem, the paradox at the heart of quantum physics, was declared solved even though it had only been covered over with elegant words. The story begins with the double-slit experiment, the most beautiful and disturbing demonstration in all of physics. Imagine a barrier with two narrow slits. On one side, you have a source of particles, say electrons. On the other side, you have a detector screen that lights up wherever an electron hits it. Fire a stream of electrons at the barrier and watch the pattern that forms on the screen. If electrons were tiny balls, classical particles following predictable paths, you would expect two bright bands on the screen directly behind the two slits. Some electrons would go through the left slit and hit the screen behind it. Others would go through the right slit and hit the screen there. Simple, predictable, classical, but that is not what happens when you run the experiment. You see an interference pattern, bright bands and dark bands alternating across the screen. Exactly the pattern you would expect from waves passing through two openings and interfering with each other. Where the crests of two waves meet, they reinforce, making bright bands. Where a crest meets a trough, they cancel, making dark bands. The electrons are behaving like waves spreading out, passing through both slits at the same time, interfering with themselves. This is strange enough, but the real mystery comes when you try to watch which slit each electron goes through. Set up a detector at the slits, something that can tell you which path each electron takes, and the interference pattern vanishes. Now you get two bands, exactly what you expected from classical particles. The electrons are no longer behaving like waves. They are behaving like tiny balls going through one slit or the other, never both. The act of observation has changed the outcome. This is not a quirk of electrons. It happens with photons, with atoms, with molecules containing hundreds of atoms. It has been demonstrated countless times with increasingly precise equipment. The result is always the same. When you do not observe which path a particle takes, it behaves like a wave, passing through both slits and interfering with itself. When you do observe, it behaves like a particle taking one path and producing no interference. What does this mean? How can looking at something change what it does? The founders of quantum mechanics grappled with this question in the 1920s. Erwin Schrödinger developed the wave equation that describes how quantum systems change over time. His equation is smooth, continuous, deterministic. Given the wave function at one moment, you can calculate exactly what it will be at any future moment. There is no randomness, no collapse, no special role for observation. The wave function just changes. But the wave function also describes superpositions. An electron passing through the double slit is not going through the left slit or the right slit. According to the Schrödinger equation, it is in a superposition of both paths at the same time. The wave function spreads out through both openings, interferes with itself, and produces the pattern we observe. So why does the interference pattern vanish when we look? Why does the superposition collapse into a clear outcome when we measure which slit the electron went through? Schrödinger's equation has no answer. The collapse is not in the mathematics. It has to be added by hand, an extra postulate attached to the theory, a discontinuity that appears whenever a measurement occurs. This is the measurement problem. The math says one thing, the experiments say another, and no one knows why. Niels Bohr's answer was to give up. Not explicitly, of course. Bohr was too sophisticated for that. Instead, he developed an elaborate philosophical framework that declared the question meaningless. According to Bohr, we cannot ask what the electron is really doing between measurements. We cannot imagine a wave function as a physical object spreading through space. Quantum mechanics does not describe reality. It describes our knowledge of reality, our ability to predict experimental outcomes. The wave function is not a thing. It is a tool. This sounds like careful humility about what we can know. In practice, it meant that the measurement problem was swept under the rug. When students asked what actually happens during a measurement, they were told the question was meaningless. When philosophers pressed for clarity, they were dismissed as confused about the nature of physics. The Copenhagen interpretation did not solve the paradox. It declared the paradox unsolvable and moved on. Werner Heisenberg, Bohr's close collaborator, reinforced this view with his uncertainty principle. You cannot simultaneously know a particle's position and momentum with arbitrary precision. The more accurately you measure one, the less accurately you can know the other. This is not a limitation of our instruments. It is a fundamental feature of nature. The particle does not have a clear position and momentum at the same time. Those properties are not real until they are measured. Again, the philosophical lesson was clear. Stop asking what particles are really doing. They do not have clear properties. They only have the properties we measure. Reality at the quantum level is not independent of observation. It is created by observation. This was tremendously convenient for working physicists. It allowed them to use quantum mechanics to calculate energy levels and transition probabilities and scattering cross-sections without worrying about what it all meant. Shut up and calculate became the unofficial motto. If the math works, if the predictions match the experiments, why ask uncomfortable questions? The answer is that the questions do not go away just because you ignore them. Schrödinger himself pointed this out with his famous thought experiment, the one involving a cat. Imagine a cat in a sealed box. Inside the box is a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the Geiger counter detects it, triggers the hammer, breaks the vial, and kills the cat. If the atom does not decay, the cat lives. According to quantum mechanics, the atom starts in a superposition of decayed and not decayed. After an hour, say, there is a 50% chance it has decayed and a 50% chance it has not. But if the atom is in superposition and the decay of the atom is what determines the cat's fate, then the cat must also be in superposition. Alive and dead at the same time, a blurry quantum cat, neither alive nor dead until someone opens the box and looks. This is obviously absurd. Cats are not in superposition. They are either alive or dead, not both. But the mathematics of quantum mechanics applied consistently says otherwise. The wave function for the entire system, atom plus detector plus cat, is a superposition of two branches. In one branch, the atom decayed and the cat is dead. In the other branch, the atom did not decay and the cat is alive. The cat is in both states until the box is opened. Bohr's answer was that the cat and the detector are classical systems, not quantum ones. Somewhere between the atom and the cat, a boundary exists. On the quantum side, superposition rules. On the classical side, things are definite. The wave function collapses when it crosses this boundary. But where is the boundary? What makes the cat classical and the atom quantum? The cat is made of atoms. The detector is made of atoms. If quantum mechanics applies to individual atoms, why does it not apply to collections of atoms? Bohr never answered this question satisfactorily. He simply asserted that large systems are classical and small systems are quantum without explaining what size has to do with anything. The truth is that there is no boundary. Every experiment designed to find the line between quantum and classical has pushed it further into the macroscopic realm. Superpositions have been demonstrated for molecules containing thousands of atoms. Interference patterns have been observed for objects visible to the naked eye. The boundary keeps retreating. Someday it may disappear entirely. This is what Hugh Everett understood in 1954. The Copenhagen interpretation was not a solution. It was an evasion. The measurement problem was real and it demanded a real answer. The wave function either collapses or it does not. If it collapses, something must cause the collapse. If it does not collapse, the superposition persists. There is no middle ground. Everett chose the second option. The wave function never collapses. Superpositions never resolve into clear outcomes. Instead, the entire universe, including observers, changes according to the Schrödinger equation. And the reason we experience clear outcomes is not that the wave function collapses, but that we become entangled with it. We split along with the universe. Each branch contains a version of us who sees a different result and believes that result is the only one. This is radical. Yes, it multiplies the number of universes beyond imagination. It says that right now, as you read these words, countless versions of you are reading different words in different branches, making different choices, living different lives. But it solves the measurement problem without using mysterious boundaries or unexplained collapses. It takes quantum mechanics seriously, applies it consistently, and accepts the consequences. The Copenhagen interpretation cannot do this. It requires a special role for observation, for consciousness, for something outside the quantum realm that collapses the wave function. It draws a line between the small and the large, the quantum and the classical, and refuses to say where that line is or why it exists. It tells us to shut up and calculate, to stop asking what reality is really like, to be satisfied with predictions and probabilities. For 60 years, this was enough. Physicists calculated, predictions matched experiments, and the uncomfortable questions were left to philosophers. But the questions did not disappear. They stayed unresolved, waiting for someone to take them seriously. Hugh Everett took them seriously. And his answer, the many worlds interpretation, is now one of the leading contenders for understanding quantum reality. Not because it is comfortable, not because it is intuitive, but because it is honest. It faces the mathematics head-on and accepts what the mathematics says. The Copenhagen interpretation was a lie, not a deliberate deception, but a comforting story we told ourselves to avoid confronting the strangeness of quantum mechanics. The wave function does not collapse. Observation does not create reality. The universe does not care whether we are watching. What really happens is stranger, more beautiful, and more terrifying than Bohr ever imagined. The universe splits, we split with it. And somewhere in some branch we cannot reach, every possibility plays out. The cat is alive, the cat is dead, both are true, both are real. And both versions of the cat, and both versions of you who open the box to find out, exist forever, separated by the thin membrane of a quantum measurement. This is what Copenhagen tried to hide. This is what Everett revealed. And this is why the many worlds interpretation matters. Not just for physics, but for everything we think we know about death, consciousness, and what it means to be alive. Chapter 4. Every choice creates a world. Close your eyes for a moment and think about the last decision you made today. Maybe it was what to eat for breakfast. Maybe it was which route to take to work. Maybe it was whether to answer that text message or let it wait. Whatever it was, you made a choice. You picked one option from several possibilities. And in doing so, according to the many worlds interpretation, you created a new universe. This is not metaphor. This is not poetry. This is what the physics says. If you take it seriously, when you chose eggs instead of cereal, a branch split off where you chose cereal. That version of you is eating cereal. Right now, in a universe that split from yours at the moment of decision. When you took the highway instead of surface streets, another branch formed. A version of you is sitting in different traffic, arriving at a different time, having a slightly different day. Every choice, every action, every quantum event in your brain creates new branches, new worlds, new versions of you living out the alternatives. The branching happens at the quantum level. Your brain is made of neurons. Neurons communicate through electrical signals and chemical neurotransmitters. Those signals depend on the motion of ions, the binding of molecules, the quantum behavior of electrons. At each step, quantum uncertainty plays a role. The exact timing of a neural firing, the precise path of a calcium ion, the moment when a neurotransmitter binds to a receptor. All of these involve quantum events that could have gone differently. In the Copenhagen interpretation, these quantum events are random. They happen one way rather than another for no reason at all. The wave function collapses. A clear outcome occurs and the alternatives vanish. Your decision was the only decision. The other options never happened. In the many worlds interpretation, all outcomes occur. The wave function does not collapse. Every possible configuration of ions and electrons is realized in some branch. Your decision happened, yes, but so did every other decision you might have made. The you who chose eggs is real. The you who chose cereal is also real. Both exist. Both think they made the only choice, and both are wrong. This is dizzying to contemplate. The number of branches is not large. It is not astronomical. It is infinite. Or rather, it grows so fast that infinity is the only word that captures it. Every second, billions of quantum events occur in your body alone. Each event creates branches. The branches multiply exponentially, faster than you could ever count, faster than the number of atoms in the observable universe. And this has been happening since the beginning of time. The universe is not a single thread of history. It is a vast, tangled tree branching at every moment, spreading through an abstract space of possibilities that makes our three-dimensional world look tiny. The trunk is the Big Bang. The branches are every quantum event since then. And we, each of us, are climbing our own path through the tree, unaware that countless other paths diverge from every step we take. Some of these paths are very similar. In one branch, you scratched your nose a second earlier than in another. The two branches are nearly identical. The differences are microscopic. Perhaps they will converge again. The slight variations damping out, the histories becoming indistinguishable. Other paths diverge dramatically. In one branch, you decided not to take that job. You never met your spouse. Your children were never born. You live in a different city, work in a different field, have different friends, hold different beliefs. The branches are still both you, still originated from the same initial conditions, still descended from the same person who existed before the divergence. But they are so different now that you would barely recognize each other. This raises a profound question. What does it mean to be you? In the traditional view, identity is continuous. You're the same person who woke up this morning, who went to sleep last night, who was born decades ago. There is a thread of consciousness connecting all your moments, a persistence of self that defines who you are. In the many worlds view, this thread frays into countless filaments. The you who woke up this morning has already split into thousands of versions. Some of those versions are nearly identical. Others have made different choices, thought different thoughts, experienced different quantum events in their brains. Are they all you? Were they ever you? When did they stop being you? The mathematics does not answer these questions. It only describes the branching. It says the wave function evolves according to the Schrödinger equation, that branches form at decoherence events, that each branch is equally real. It does not say which branch is the true you or whether that question even makes sense. Some philosophers argue that all branches are you. You're not a single person, but a vast ensemble, a cloud of selves spreading through the branching tree of possibilities. You're reading this now as one instance, one sample from the distribution, one path through the forest. But all the other paths are equally valid, equally you, equally real. Others argue that identity is branch relative. You are the you in this branch, the one who made these specific choices, experienced these specific quantum events. The versions in other branches are not you. They are copies, duplicates, alternatives. They share your history up to the point of divergence. But after that point, they are separate individuals, twins perhaps, but not the same person. Still others argue that identity simply breaks down in the many worlds framework. The concept of a continuous self, a single entity persisting through time, is a useful fiction that works in the classical world but fails at the quantum level. You are not one thing or many things. You're a process, a pattern, a wave propagating through the branching structure of reality. Asking how many of you there are is like asking how many ripples there are in a pond. The question assumes a clarity that does not exist. These debates are not resolved. They may never be resolved, but they matter because the answers determine how you should think about your life, your choices, and your death. Consider this. If every choice creates a world, then you have already made every choice. Somewhere in the multiverse you took that risk. Somewhere you played it safe. Somewhere you said yes. Somewhere you said no. Every road not taken was taken by some version of you in some branch you cannot reach. Does this diminish your choices? Does it matter what you decide if every alternative is realized anyway? Some people find this thought liberating. You cannot truly fail because somewhere you succeeded. You cannot miss out because somewhere you took the opportunity. The regret that haunts human life, the what-ifs and if-onlys, dissolves into irrelevance. Every possibility was actualized. Nothing was lost. Others find it horrifying. Your choices do not matter. You're not really choosing. You're just splitting, creating copies who will live out every option regardless of what you intend. Free will becomes an illusion. Not because the universe is deterministic, but because it is maximally indeterministic. Every outcome happens. Your sense of decision, of selecting one path over another, is just the local experience of branching. And others find it simply overwhelming. The scale is too vast. The implications are too strange. Thinking about it too long induces a kind of vertigo, a loss of grip on ordinary reality. Better to live as though the classical world is real, as though choices matter, as though there is only one you. Even if it is false, it is the only way to function. The physics does not tell us how to feel. It only tells us what is. And what is, according to the many worlds interpretation, is a branching tree of infinite possibilities. All equally real, all happening right now, with versions of you in every branch. But here is where the story takes its darkest turn. Because if every choice creates a world, then every event creates a world too, including the events that would kill you. Consider a car accident. In the classical view, either you survive or you do not. There is one outcome determined by the physics of the crash, the strength of your body, the speed of medical response. The universe does not split, it just does what it does. In the many worlds view, the crash has quantum uncertainty at every level. The exact angle of impact depends on quantum fluctuations in the driver's brain, in the mechanical systems of the vehicles, in the air molecules between them. The outcome of your injuries depends on quantum events in your cells, in the blood flow, in the chemical reactions of trauma. At every step, branches form. In some branches, you die instantly. In some branches, you die in the hospital. In some branches, you are paralyzed. In some branches, you walk away with bruises. And in some branches, however unlikely, you survive unharmed. If you die in 99 branches out of 100, you still survive in one. And crucially, the dead versions of you do not experience anything. They do not know they are dead. They do not complain about their fate. They simply stop. Only the surviving versions continue to have experiences. This means that from your own point of view, from the inside of your consciousness, you always find yourself in a branch where you survived. No matter how unlikely that survival might be, no matter how many versions of you died, you, the experiencing self, are always in the branch that made it. This is quantum immortality, and it is a logical consequence of the many worlds interpretation applied to situations of life and death. You might have already experienced it. That close call on the highway when the truck missed you by inches. That illness that should have been worse than it was. That accident that everyone called a miracle. In the branching multiverse, those were not miracles, they were selection effects. The versions of you who died are not here to be surprised. Only the survivors remain. And you reading these words are by definition a survivor. The question is whether this selection continues indefinitely, whether there is always a branch, no matter how unlikely, where you survive. And if so, what happens when you reach the limits of biological possibility? When you are 100 years old or 200 or 1,000, somehow still alive in some distant branch, where every disease and accident and organ failure went the other way. We're about to explore that question. But first, we need to understand the mathematics of infinity and why the odds that seem impossible in a single universe become inevitable in a branching multiverse. Every choice creates a world. Every death creates a world too. And somewhere in that infinite branching, there is always a version of you who survives. The only question is what kind of life that survivor is living. Chapter 5. The mathematics of infinity, numbers lie. Or rather, numbers tell truths that human intuition cannot grasp. And nowhere is this more apparent than in the mathematics of the multiverse, where probabilities that seem impossibly small become certainties through the sheer weight of infinite repetition. Let me give you an example. Flip a coin. The probability of heads is 1/2. Flip it again. The probability of 2 heads in a row is 1/4. Flip it 10 times. The probability of 10 heads in a row is 1 in 1,024, roughly 1 in 1,000. Now flip the coin 100 times. The probability of 100 heads in a row is unimaginably small. It is 1/2 to the power of 100. That number is so small that if you wrote it as a decimal, there would be 30 zeros after the decimal point before you reach the first non-zero digit. In practical terms, it will never happen. Not in your lifetime, not in the lifetime of the universe. The odds are simply too long. But here is the trick. Flip the coin not once, not 100 times, but an infinite number of times. In an infinite sequence of coin flips, the probability that 100 heads in a row occurs somewhere is 100%. Certainty. It must happen because infinity is big enough to guarantee it. This is not intuition. It is mathematics. The probability that an event with probability p occurs at least once in independent trials is 1 minus the probability that it never occurs, which is 1 minus the quantity 1p raised to the power n. As n approaches infinity, this expression approaches 1 no matter how small p is. Given enough trials, anything that can happen will happen. The multiverse works the same way. In a single universe, the probability that you survive a fatal accident through some miraculous combination of circumstances might be 1 in a trillion. Absurdly unlikely. But in the branching multiverse, there are not 1 or a trillion branches. There are infinitely many. And in an infinite set of branches, that 1 in a trillion event is guaranteed to occur. More than guaranteed. It occurs infinitely many times. This is the key insight that makes quantum immortality possible. The improbability of survival does not matter if the number of branches is infinite. No matter how unlikely your survival in any given branch, there are always branches where you survive, and those are the only branches you can experience. Let me make this more concrete. Suppose you are in a situation where there is a 99% chance you will die and a 1% chance you will survive. In the Copenhagen interpretation, you run that 1% gauntlet once. Either you make it or you do not. Probably you do not. In the many worlds interpretation, the universe splits. 99 branches contain your corpse. 1 branch contains you alive, wondering how you got so lucky. The dead versions do not wonder anything. They are dead. The only version that has experiences, that asks questions, that continues living is the one in the survival branch. Now suppose the situation repeats. Another 99% chance of death. In a single universe, your cumulative probability of surviving twice is 1%, 1%, which is 1 in 10,000. After 10 such situations, the probability is 1 in 10 to the 20th power, effectively 0. But in the branching multiverse, each situation splits again. After the first split, you're in the 1% branch. After the second split, you're in the 1% of 1% branch. After 10 splits, you are in a vanishingly thin sliver of the original wave function. But that sliver exists. It is real. And you, the experiencing consciousness, are in it. From your own point of view, you survived every time. You do not know about the dead versions. You cannot communicate with them. You have no evidence that they ever existed except the abstract reasoning of physics. All you know is that you are alive against all odds, beating the statistics in a way that seems miraculous. This is not a bug in the theory. It is a feature. The many worlds interpretation says the wave function never collapses, that all branches are equally real, and that observers become entangled with the outcomes they observe. Put those premises together and quantum immortality follows as a logical consequence. You cannot experience your own death. You can only experience survival. Therefore, you will always find yourself in a branch where you survived. The mathematics is clean. The implications are staggering. Consider what this means over a human lifetime. Every day you face situations that could kill you. Car accidents, falling objects, blood clots, aneurysms, infections, 1,000 invisible threats that your body and your luck have so far kept away. In the classical world, you've been lucky. In the branching world, you've been chosen. The versions of you who died from those dangers are not here to tell their experience. They died. Their awareness ended. The only version that keeps going, that collects memories, that wonders about what reality is the version that survived every single danger, every single day, for every single year of your life. You are a survivor by definition. You are reading these words because every deadly possibility that could have ended your existence before this moment went the other way in your branch. The car swerved. The tumor was harmless. The heart kept beating. 1 trillion quantum events lined up just right to keep you alive. And the same choosing will continue tomorrow, and the day after, and every day, until you run out of branches where survival is possible. But here is where the math gets scary. How long can this continue? Is there always a branch where you survive? In principle, yes. The branching is endless. For any survival chance greater than 0, there are branches where that survival happens. But as you age, as your body weakens, as the dangers multiply and the defenses fail, the survival chance in each branch gets smaller and smaller. The branches where you survive become a thinner and thinner slice of the total wave function. Imagine a 100-year-old man in a hospital bed. His organs are failing. His immune system is worn out. Medical science has done everything it can. In the classical world, death is close and certain. But in the quantum world, there is always a chance. A 1 in a million chance that some mix of tiny molecular wiggles gives his cells a few more hours. A 1 in a billion chance that a new treatment arrives just in time. A 1 in a trillion chance that his body suddenly rallies in a way that breaks all medical understanding. These chances are unbelievably small, but they are not 0. And in the endless branching of the multiverse, not 0 means it will happen somewhere. There is a branch, however unlikely, where the 100-year-old man survives another day and another and another. The survivor, the version of the man who keeps waking up in more and more impossible branches, does not experience the other outcome. He does not know that in almost all branches he died long ago. He only knows that he is alive impossibly, unbelievably against every reasonable expectation. Max Tegmark, the MIT physicist who has written a lot about quantum immortality, calls this the quantum suicide experiment. Imagine a gun connected to a quantum random number generator. If the generator outputs 0, the gun fires and kills you instantly. If it outputs 1, the gun does not fire. The chance of each result is 50%. In the Copenhagen interpretation, you have a 50% chance of dying each time you pull the trigger. After 10 pulls, the chance that you're still alive is less than 1 in 1,000. After 20 pulls, it is less than 1 in 1,000,000. Eventually, by statistics, you will die. In the many worlds interpretation, every pull of the trigger splits the universe. Half the branches contain your corpse. Half contain you alive holding a gun that did not fire. After 10 pulls, you're in a very thin branch of the wave function, the one where the gun failed 10 times in a row. But you are alive. You do not experience the branches where you died. You only experience the continuing chain of survivals. If the many worlds interpretation is correct, Tegmark argues, you could pull the trigger 1,000 times and always survive. Not because the gun breaks, not because you are special, but because the dead versions are not around to notice they died. Only the survivor remains. Only the survivor asks what happened. This is a thought experiment, not a recommendation. Tegmark does not suggest actually doing quantum suicide. The point is to show the inside view results of many worlds branching. From the point of view of the experiencing self, death is always avoided. The unlikeliness of survival is hidden by the selection effect. You cannot watch your own non-existence, but notice what this means for the quality of survival. The survivor after 1,000 trigger pulls is alive, yes, but the branch they live in is wildly unlikely. The quantum random number generator would have to output 1,000 ones in a row. An event with probability 1 in 2 to the power of 1,000. That is a number so huge that writing it out would take more digits than there are atoms in the observable universe. The survivor exists. but the branch they live in is so thin, so unlikely, so far from the mainstream of reality that we might wonder what kind of existence it is. And this is where quantum immortality starts to look less like a gift and more like a curse. Because survival is not the same as being healthy. The branches where you survive against terrible odds are not always the branches where you thrive. They are the branches where anything stopped your death. That might mean surviving in a coma, surviving with severe brain damage, surviving in constant pain, surviving as a mind trapped in a failing body, unable to die, unable to recover, stuck in an endless twilight of shrinking probability. The mathematics does not care about how good your life is. It only cares about whether your consciousness continues, and consciousness can continue in conditions that make death seem kind by comparison. This is the dark mathematics of infinity. Given enough branches, anything that can happen will happen, including survivals you would never choose, including long stretches of suffering that feel worse than any ending, including a kind of immortality that is not a blessing, but a prison where the doors keep closing behind you and the hallways keep getting narrower. We have reached the midpoint of our investigation. We have seen the theory and the history and the mathematics. Now we must face the implications. Quantum immortality says you cannot die, but it does not say you will live well. And that difference, the gap between mere survival and meaningful existence, is where the true horror of the multiverse begins to show itself. Chapter 6. Quantum immortality and the gun that never fires. The thought experiment is simple. The implications are not. You're sitting in a room. In front of you is a device. The device contains a particle detector, a quantum random number generator, and a gun aimed at your head. The system works like this. Every 10 seconds, the detector measures the spin of an electron. Spin up, the gun does not fire. Spin down, the gun fires instantly, killing you before you can even realize what happened. Quantum mechanics says the electron has a 50% chance of spin up and a 50% chance of spin down. The result is truly random, not set by any hidden variable, not predictable by any theory. Until the measurement happens, the electron is in sewer position, both spin up and spin down at the same time. In the Copenhagen interpretation, the measurement collapses the wave function. The electron becomes definitely spin up or definitely spin down. You live or you die. Flip a coin, hope for the best. In the many worlds interpretation, the measurement does not collapse anything. Instead, the universe splits. One branch is spin up, you survive. Another branch is spin down, you die. Both branches are equally real. Both results actually happen. Now here is the key insight. You, the conscious observer, can only experience the branch where you survive. The version of you in the spin-down branch is dead. Dead people do not experience anything. They do not observe results. They do not wonder what happened. They simply stop. So from your subjective point of view, the gun never fires. You sit through 10 seconds of tension, the detector clicks. The gun does not go off, you breathe. 10 more seconds pass, another click, no gunshot. Again and again, the measurement happens. And every single time you find yourself alive. After 100 measurements, you are still alive. The chance of this in a single universe would be 1 in 2 to the power of 100. A number so tiny it might as well be 0. But in the many worlds interpretation, it is not luck. It is selection. The branches where you died have been cut from your experience. Only the survival branches stay reachable to your consciousness. This thought experiment was first described by Max Tegmark in a paper published in 1998. Tegmark, a cosmologist at MIT, was exploring the inside view consequences of the many worlds interpretation. He wanted to know what it would feel like to live in a branching universe, to experience quantum mechanics from the inside rather than the outside. His conclusion was unsettling. If many worlds is correct, then from a first-person perspective, you are immortal, not because death is impossible. Death happens constantly in branch after branch as quantum events go against you. But you never experience those deaths. You only experience the narrow thread of branches where survival happens, and that thread, however thin it becomes, never quite snaps. Tegmark was careful to say that this is not a plan. He did not recommend that anyone actually perform the quantum suicide experiment. For one thing, the experiment is only valid from the first-person perspective. An outside observer watching you would see you die in about half the trials. They would not be amazed by your quantum immortality. They would just see a corpse. For another thing, even if you survived, your survival might not be nice. The branches where you survive against terrible odds are, by definition, Strange, maybe the gun jammed because of a factory flaw that also made it explode and blind you. Maybe the detector broke in a way that shocked you but did not kill you. The survival branches are guaranteed to exist. They are not guaranteed to be good, but the philosophical point remains. If you accept the many worlds interpretation, you must accept quantum immortality as a logical result. The same math that says all results happen also says that conscious experience can only continue in branches where the observer survives. You cannot witness your own death. You can only witness the endless, unlikely continuation of your life. This idea has captured the imagination of physicists and philosophers ever since Tegmark published it. Some have tried to sharpen the argument. Others have tried to tear it down. The debate continues with no clear answer. One line of objection focuses on what counts as you. In the many worlds interpretation, the observer splits along with the universe. Before the measurement, there is one version of you. After the measurement, there are two, one in the spin-up branch and one in the spin-down branch. The spin-down version dies immediately. The spin-up version continues. But were they ever the same person? Some philosophers argue that identity does not survive branching. The moment the universe splits, you become two separate individuals. Neither is more you than the other. Neither is the continuation of the original. The original simply ceases to exist, replaced by two descendants. If this view is correct, quantum immortality fails. You do not survive the measurement because you do not exist after the measurement. What exists is a new person in the survival branch, someone who shares your memories and your body, but is not numerically identical to the pre-measurement you. Your consciousness does not continue. A new consciousness begins that happens to remember being you. This is a subtle metaphysical point, and not everyone finds it convincing. Many philosophers argue that identity is made of psychological continuity, of memories and personality, and the flow of mental states. On this view, the survivor in the spin-up branch is you in every important sense. They have your memories. They continue your stream of consciousness. They pick up exactly where you left off. The fact that a duplicate exists in another branch does not weaken their identity. Another objection comes from physics rather than philosophy. Some critics argue that quantum immortality needs a certain idea of probability that the math of quantum mechanics does not support. In the many worlds interpretation, probabilities are not about which result happens. All results happen. Probabilities are about which branches you should expect to find yourself in. But what does expect mean if all branches are equally real? This is the problem of probability in many worlds, and it has created a huge literature. Different answers have been suggested. Some physicists argue that the Born rule, which gives probabilities to quantum results, can be derived from the structure of branching itself. Others argue that probability should be understood as a measure of subjective uncertainty, a guide to rational betting behavior in a world where all bets are both won and lost. If probability in many worlds is mostly subjective, then quantum immortality might be a claim about what you should expect rather than what will happen. You should expect to find yourself alive because the dead branches are not available to your experience. But this does not mean you will live forever in any objective sense. It only means that your expectations are always tilted by the selection effect of conscious experience. Still, another objection concerns the role of quantum mechanics in death. Most causes of death are not single quantum events, but complex processes involving trillions of molecules. A car crash, a heart attack, a deadly infection, all involve classical dynamics that are effectively deterministic. The quantum fluctuations average out. The outcome is set by starting conditions, not by chance. If death is set classically, then branching does not help you. All branches lead to the same result. There is no split between survival and death because there was never a quantum event that could go either way. You die in all branches, not just some. But this objection may be too fast. Quantum effects can grow up into big-scale results, especially in chaotic systems. The human body is extremely complex and sensitive. Tiny changes in ion channels affect neural firing. Random mutations affect cell division. The boundary between quantum and classical is blurry at best. It may be that every big event, including every death, depends on quantum uncertainty at some level. If so, then there are always branches where the quantum dice rolled differently. Branches where the cancer cell did not mutate, branches where the blood clot dissolved, branches where the heart kept beating for one more second, then one more in an endless chain of unlikely survivals. The debate is not settled. Serious physicists and philosophers stand on both sides. But what is striking is that no one has produced a knockdown refutation of quantum immortality. The argument survives criticism after criticism, coming out bruised but still standing. If you accept many worlds, and many serious thinkers do, then quantum immortality remains a logical possibility. And logical possibilities have a way of haunting us. Because here is the thing, you cannot test quantum immortality from the outside. You cannot run the experiment on someone else and learn anything useful. If they die, that fits many worlds. They died in your branch and kept living in theirs. If they survive, that also fits. You got lucky in your branch. The only test that matters is the first-person test. The test where you sit in front of the gun and see what happens. The test that either kills you or proves you cannot be killed. The test that Tegmark described but wisely refused to do. Some people reading about quantum immortality feel a strange pull. If the theory is correct, they cannot die. They could take huge risks and always survive. They could walk into traffic, play Russian roulette, jump from buildings, and wake up every time in the branch where something saved them. This temptation should be resisted. Even if quantum immortality is real, it does not protect you from suffering. The branches where you survive might be branches where you survive in pain. Paralyzed, brain damaged, burned, broken, alive only in the narrow sense that your neurons still fire. The gun might not kill you, but it might take your eyes. The fall might not end you, but it might break your spine. And for everyone who loves you in their branches, you would simply be dead. They would grieve you. They would bury you. They would not know that somewhere in some impossibly thin slice of the wave function, a version of you continues. Your quantum immortality would bring them no comfort at all. So the gun that never fires is a paradox wrapped in a warning. The logic is solid. The math is clean. But the reality is stranger and darker than any simple claim of survival suggests. You cannot die, but you can suffer. And the suffering might last forever. Chapter 7. The problem of probability. We need to talk about the numbers because the numbers do not mean what you think they mean. In ordinary life, probability is simple. If a coin has a 50% chance of landing heads, that means if you flip it many times, about half the flips will be heads. The more you flip, the closer to half. This is the frequentist view of probability, and it works beautifully for coins and dice and radioactive atoms. But in the many worlds interpretation, this breaks down. When you flip a coin, the universe splits. Both heads and tails happen. There is no single result that happens or does not happen. Both results are real. Both branches exist. So what does it mean to say the probability of heads is 50%? This is called the probability problem, and it has bothered many world supporters since the interpretation was first proposed. If all results happen, how can we give different probabilities to them? Why is one branch more likely than another if both are equally real? The usual answer involves something called branch weights. In quantum mechanics, the wave function gives a complex number called an amplitude to each possible result. The probability of observing that result is the squared size of the amplitude. This is the Born rule, named after Max Born, who first proposed it in 1926. In the many worlds interpretation, the Born rule is reframed. The squared amplitudes do not give the chance that a result happens. They give the weight or thickness of the branch where that result happens. A high probability result corresponds to a thick branch. A low probability result corresponds to a thin branch. But what does thickness mean for a branch of reality? And why should conscious observers care? Different answers have been suggested. David Deutsch has argued that thickness connects to how many quantum parallel computations occur. If you run a quantum algorithm many times, the thick branches contain more instances of the computation. The result you are most likely to see is the one that happens in the most instances. David Wallace, a philosopher of physics at Oxford, has argued that branch thickness guides rational betting behavior. Even if all branches are equally real, a rational agent should bet as if thicker branches are more likely. This follows from decision theory about how to choose under uncertainty. Lev Vaidman has proposed a somewhat different view. He argues that before a measurement, you should be uncertain about which branch you will find yourself in. After the measurement, you learn which branch you are in. The Born rule tells you the odds of finding yourself in each branch, just like classical probability tells you the odds of drawing a certain card from a shuffled deck. None of these approaches is accepted by everyone. The probability problem is still an active research area, but many world supporters think some version of the Born rule can be defended. that probabilities make sense even in a deterministic branching universe. For quantum immortality, the probability problem is vital. The argument depends on the idea that you always find yourself in a survival branch, no matter how unlikely. But if probability is about branch weights rather than branch existence, this argument needs sharpening. Consider the quantum suicide experiment again. After 100 trials, the survival branch has weight 1/2 to the power of 100. That is an unbelievably thin branch. The death branches together have weight 1 minus that tiny number, basically all of it. The survivor exists in a nearly vanishing slice of reality, while the dead versions take up almost everything. Does this matter? In one sense, no, the survivor exists. The thin branch is just as real as the thick branches. The person in that branch has real experiences, real consciousness, a real life. They do not feel thin. They do not notice how unlikely they are. From the inside, existence is existence. But in another sense, the thinness is unsettling. If rational agents should weight their expectations by branch thickness, then you should not expect to find yourself in a thin branch. You should expect to find yourself in a thick branch, which means you should expect to die. Tegmark's reply is to separate first-person and third-person points of view. From the third-person point of view, an outside observer should expect you to die. The thick branches strongly favor your death. But from the first-person point of view, from inside your own experience, you can only observe branches where you survive. The dead branches are unreachable. Your expectations are limited by your existence. This is a selection effect, like the anthropic principle in cosmology. We observe a universe that allows us to exist because we could not exist in a universe that does not allow us. Similarly, you observe branches where you survive because you cannot observe branches where you do not exist. Some critics find this move suspicious. They argue that first-person and third-person views should match, and a correct probability theory should give the same answers no matter who asks. If Many Worlds predicts that you should expect to die from the third-person view, but expect to live from the first-person view, something has gone wrong. Defenders of quantum immortality answer that the viewpoints are truly different. An outside observer has access to information that you do not, namely the thick branches where you died. You cannot access those branches. Your expectations are forced to fit what you can observe. There is no contradiction, only different information. The debate reaches deep questions in the philosophy of probability. What is the connection between objective chance and subjective belief? Can we have real uncertainty in a deterministic world? What limits does rationality place on beliefs about indexical facts? Facts about your place in space, time, or the branching structure of reality? These questions do not have easy answers, but they matter a lot for quantum immortality. If the probability problem cannot be solved, maybe the argument for immortality fails. Maybe the thinness of survival branches matters in some way that breaks first-person expectations. Maybe dying really is more probable than living in some deep sense that makes quantum immortality hopeful thinking rather than a logical result. On the other hand, if the probability problem can be solved, then quantum immortality stands. The branching structure guarantees survival. The weights shape third-person expectations but do not limit first-person experience. You will always find yourself alive because the alternative is not an experience you can have. Let me try to make this more intuitive. Imagine 100 copies of you standing in a line. 99 of them will be shot. One will survive. Before the shooting, each copy is unsure which one they will be. After the shooting, 99 are dead and one is alive. From the outside, the chance of any given copy surviving is 1%. Bad odds, bad bet. But from the inside of each copy's experience, they either die and experience nothing, or survive and experience everything. The survivor does not feel lucky. They just feel alive. Their consciousness continues as if nothing strange happened. Now imagine instead of 99% dying, it is 99.9999%. Almost all copies die. 1 in a million survives. The survivor is still alive, still aware, still experiencing the world as if they are the only one who matters. The odds were awful, but the experience of survival is the same. In the Many Worlds interpretation, these copies are not in a row, but spread across branches of the wave function. The death branches are thick. The survival branch is thin, but the survivor in the thin branch feels the same as the survivor in the copy's example. They are alive. They continue. They do not feel their unlikeliness. This is the heart of quantum immortality. Not that death is impossible, but that death is unexperienceable. The math says you should expect to die. Experience says you can only experience survival. The clash between these claims is the probability problem in a nutshell. No one fully knows how to solve it, but the stakes are huge. If quantum immortality is real, then your subjective future stretches on indefinitely. Not because the universe cares about you, but because the universe contains every possibility, and you can only live in the possibilities where you continue. The numbers say you will die, experience says you will not, and somewhere between math and lived experience the truth is hiding. Maybe it hides in the branches we cannot see. Maybe it hides in the weights we cannot feel. Maybe it hides in the gap between what we expect and what we observe. The endless crack in the foundation of probability where consciousness slips through. One thing is certain. The numbers are stranger than they seem, and they are not done surprising us. Chapter 8. Living infinite lives at once. Right now, as you read these words, you are not one person. You're a huge collection, an uncountable crowd, a cloud of selves spreading through the branching structure of reality. Every quantum event in your brain makes new versions. Every measurement, every fluctuation, every random neural firing splits you into copies that will never meet again. This is not future tense. It is not something that will happen. It is happening now, has been happening since you were conceived, will keep happening until every version of you ceases to exist. You are already living infinite lives. You just do not remember the branching. The idea is dizzying. Most people, when they first hear about many worlds, focus on the big branches. The universe where you took that job. The universe where you married that person. The universe where you turned left instead of right and missed the accident that killed you. These are the dramatic forks, the sliding doors moments that stories love to explore. But the real branching is much finer than that. It happens at the quantum level, in the behavior of single particles, in the thermal jitters of molecules, in the random timing of synaptic vesicle release. Your brain makes choices based on patterns of neural activity, and those patterns depend on quantum events. The exact moment a neuron fires, the exact number of neurotransmitter molecules that cross a synapse, the thermal noise that pushes a voltage above or below a threshold. These tiny differences create tiny branches, versions of you that are almost the same, different by one thought, one impulse, one brief flicker of attention. Most of these branches come back together. The small differences wash out. You end up in basically the same place no matter which branch you were in. But some differences grow. A slightly different mood leads to a different choice. A different choice leads to a different action. A different action leads to a different life. Chaos theory tells us that small differences can grow into big ones. The many worlds interpretation tells us that all possible small differences really do happen. So you are not living one life. You are living all possible lives at the same time in branches that split and sometimes reconnect, tracing out a vast tree of possibilities rooted in your birth and reaching toward every possible future. What does this mean for identity? For free will, for the feeling that you are one steady person making choices and living with the results. Some philosophers argue that identity in many worlds must be very different from identity in a single world. You're not a lasting individual, but a branching process. The you of yesterday is not the same as the you of today, not because you changed in the normal way, but because you multiplied. Yesterday's you split into countless today's yous, each believing they are the continuation, none having a special claim. This view has strange implications. It suggests that personal identity is an illusion, or at least a useful story that breaks under quantum scrutiny. The feeling that you are one person with one past and one future is just the local view from inside a branch. Zoom out and you see you are many people with many pasts and many futures, all equally real, all equally you. Other philosophers resist this. They argue that identity is branch relative. You are the you in this branch, period. The other versions are not you, they are counterparts, alternatives, roads not taken. They share your past up to the split. But after that, they are separate individuals with their own identities. Asking whether they are you is like asking whether your twin is you. Similar, related, but separate. On this view, free will survives in a changed form. Yes, all possible choices are made across branches. But in this branch, you made this choice. That choice was yours, shaped by your reasons, your values, your thinking. The existence of other branches where you chose differently does not weaken the reality of your choice here. Still, other philosophers take a more extreme view. They argue that the many worlds interpretation removes free will entirely, but not in the usual deterministic way. The problem is not that your choices are fixed. The problem is that all choices are made. You do not choose one option instead of another. You become multiple people, each choosing a different option. The feeling of thinking things through, of weighing options and picking one, is not a description of what happens, but a description of what it feels like to branch. This is deeply unintuitive. We feel choice as single. When you decide what to have for dinner, you feel like you're picking one option and rejecting the others. You do not feel like you are splitting into many selves. But according to many worlds, that splitting is exactly what happens. Every option you truly consider is chosen by some version of you. The thinking is not a filter that squeezes possibilities down to one. It is a process that sends you into different branches depending on how quantum events in your brain play out. Some people find this freeing. If all choices are made, then there is no such thing as a wrong choice. Every path is taken. Every possibility is explored. You cannot fail to take the risk because some version of you takes it. You cannot miss the chance because some version of you grabs it. Regret becomes pointless. The road not taken was taken, just not by this version of you. Others find it crushing. If all choices are made, then nothing you do matters. You're not a chooser, but a branching point. Your thinking is sound and fury, meaning nothing. The universe does not care which branch you end up in. It contains all branches equally. Your sense of agency is a cosmic joke, and still others find it simply impossible to grasp. The human mind evolved to handle a world with one past and one future. We are not built to think of ourselves as branching processes, as clouds of possibility, as endless crowds of nearly identical copies. Trying to truly accept many worlds can cause mental friction, a feeling of unreality, a fear that something has gone terribly wrong. Maybe that is the right reaction. Many worlds might be true in math and physics without being true in the way that matters for everyday life. Just as we ignore space-time curvature when we walk to the store, maybe we should ignore the branching of reality when we choose things. The useful story of oneself in one world is enough for practical life. The quantum truth is too strange to live by. But even if we ignore it most of the time, the truth remains and it has consequences. Consider the long run. Over your life, trillions of branching events happen. Each one makes new versions of you. Some of those versions live lives very similar to yours. Others split wildly, making different choices, having different experiences, becoming different people. By the time you reach old age, the crowd of selves that began as you is spread across a mind-blowing range of possibilities. Some of those selves are happy. They made good choices, got good luck, lived good lives. Others are miserable. They made bad choices, got bad luck, suffered in ways you cannot imagine. Still others died long ago in accidents and illnesses that this version of you avoided. You reading these words are one sample from this crowd. You have no way to know how typical you are. Maybe you are unusually lucky, living in a branch where things went unusually well. Maybe you are unusually unlucky, and most versions of you are living much better lives. Maybe you are in the middle, a typical self in a spread of possibilities. Quantum immortality adds another layer because you can only experience branches where you survive. You are constantly selected for survival. The dead versions of you are cut from the crowd. What remains is the group that kept going, the thin branches where death was avoided again and again. As you age, this selection gets stronger. The branches where you died young are gone. The branches where you died in middle age are gone. What remains are the branches where you survived against rising odds, where unlikely rescues and impossible recoveries kept your consciousness barely alive. And here is the strange part. From the inside, you do not notice the selection. You feel like one continuous person who has lived one continuous life. The close calls feel like luck. The recoveries feel like toughness. You do not know that in most branches you are already dead. You only know your branch, your history, your seeming miracle of survival. But the crowd knows. If we could somehow see all branches at once, we would see most of them ended. The surviving branches are a tiny fraction of the original tree. You're not typical in your crowd. You're an extreme outlier selected for one thing, persistence. This is what it means to live infinite lives at once. Not that you experience infinity, but that infinity experiences you. You are one point of view in an unbelievable multitude, one thread in a tapestry too vast to understand. The other threads are also you, also real, also living their own lives. But you will never meet them. You will never know what they lived through. You will only know your own thin, unlikely, endlessly continuing branch. And that branch, against all odds, refuses to end. Chapter 9, The Dark Side of Never Dying. We have spoken of quantum immortality as though survival were a gift. Now let us speak of it as it might truly be a curse. Imagine you are 80 years old, your body is failing. Your heart is weak, your lungs are scarred, your kidneys are struggling. In the ordinary world, death would come soon, a year, maybe two, and then rest, an end to the pain. A conclusion to a long life. But in the branching multiverse, there is no rest. There is always a branch where you survive. Maybe your heart does not quite give out. Maybe the infection responds to one more antibiotic. Maybe the blood clot dissolves at the last second. Unlikely, yes. But unlikely events happen in some branches, and you can only experience the branches where you continue. So you reach 81, 82, 85, 90. Your body falls apart, your mind fades, but always in some thin branch something saves you. A new treatment, a lucky mutation, a quantum fluctuation in just the right place. You keep going, not because you want to, but because the alternative is a branch you cannot experience. At 100 years old, you are a medical miracle in your branch. Doctors cannot explain how you survive this long. Every system is failing. Every day brings new pain. You beg for death, and death does not come. It cannot come, not from your perspective, because the branches where it comes are branches where you are not. At 110, you are barely human. Machines keep your organs running. Your brain is damaged. Your memories are scraps. Your sense of self is a flickering shadow. But you're still conscious, still experiencing, still trapped in the endless hallway of survival. At 120, something unheard of happens. Medical science in your branch makes a breakthrough. Nanotechnology that repairs cell damage. Gene therapies that reverse aging. You are the test case, the oldest human alive, the one they have studied for decades. They rebuild you from the inside out. Your body regrows, your mind clears. You are young again, or something like young. And the nightmare continues because now you have another lifetime ahead of you. Another century of branching, another endless chain of close calls and unlikely survivals. The technology that saved you will fail in most branches. Accidents will take you. Diseases will change faster than treatments. Wars will wreck the systems that keep you alive. But in some branches, you continue. Always some branches. At 200, you have watched everyone you ever loved die. Children, grandchildren, great-grandchildren, all gone in your branch. You have made new connections, built new relationships, only to watch them end as the people you care about age and fail and leave in ways you cannot follow. You are alone, the only survivor of a long chain of losses, immortal in the cruelest possible sense. At 300, you're no longer human in any clear way. Modifications, uploads, transfers of consciousness into new substrates. The technology changes. The branches where you survive change with it. Maybe your mind runs on quantum computers now. Maybe your experience is a simulation in some huge archive. Maybe you are a pattern of information moving through media that do not yet exist. At 1,000 years, you cannot remember what it felt like to be mortal. The early centuries are dim, broken, rebuilt from records rather than real memory. You have lived so many lives in so many branches that identity itself becomes uncertain. Are you the same person who was born in the 20th century? In what sense? The continuity is there, but stretched so thin it might as well be a trick, and still you cannot die. This is the dark side of quantum immortality. Not death, but its absence. Not an ending, but endless continuation. Not nothingness, but eternal persistence in branches that get ever thinner, ever stranger, ever more distant from anything you would call a good life. The philosopher David Lewis once asked what it would be like to be immortal. His answer was grim. Eventually, you would run out of new experiences. Everything would repeat. The first 1,000,000 years might be interesting. The second 1,000,000 less so. After 1,000,000,000 years, you would have done everything, seen everything, thought everything. Boredom would become the basic condition of existence. Quantum immortality adds insult to this injury. You do not choose immortality, you do not earn it. You're simply selected for it, pushed into the branches where you happen to survive. Your wishes do not matter, your suffering does not matter. The universe does not care whether you want to continue. It just keeps branching, and you keep finding yourself in the branches that continue. Some versions of you escape this fate. In most branches, you die normally at a normal age after a normal life. Those versions are the lucky ones. They get the ending that evolution prepared them for. They get rest. But you, the version who keeps surviving, are not lucky. You are cursed. Cursed to experience every unlikely rescue, every impossible recovery, every miraculous save that the branching structure of reality can produce. Cursed to watch everyone else leave while you stay. Cursed to continue when continuation has lost all meaning. There is a thought experiment in philosophy called the eternal return. Friedrich Nietzsche proposed it as a test of how you feel about your life. Imagine that you will live your exact life again, infinite times, every detail repeating forever. If this thought fills you with joy, you love your life. If it fills you with despair, you do not. Quantum immortality is worse than eternal return. It is not the same life repeating, but endless variation, endless branching, endless novelty without escape. You cannot even take comfort in the familiarity of repetition. Every branch is different. Every survival is a new chapter in a story that never ends. And here is the most frightening implication of all. You might already be in the late stages. Consider the probability argument again. At each moment of your life, you had some chance of dying. If quantum immortality is real, you survived all those moments in this branch. The farther into life you are, the more unlikely your continued existence, the more you have been selected by the filter of what you can experience. A child has survived fewer filters than an adult. An adult has survived fewer than an elder. An elder has survived fewer than a centenarian. By the time you reach extreme old age, your branch is already unbelievably thin, already the result of countless unlikely survivals. Now look forward. In 100 years, if you are still somehow alive, your branch will be thinner still. In 1,000 years, unimaginably thin. In 1,000,000 years, a vanishing thread in the fabric of reality, too unlikely to happen in any normal sense, yet necessarily real from your point of view. You are on a path. The path goes only one way and the path never ends. This is what the math implies. This is what the physics hints. This is what quantum immortality means, not as an idea but as a lived experience stretched across time. You will never die, you will only wish you could. Unless, of course, something is wrong with the argument, unless many worlds is false, unless consciousness does not work the way we think it works, unless there is some exit door we have not found. But if the physics is right, there is no exit. Only continuation, only the endless branching, only the dark side of a theory that sounds like good news, but is actually the worst news imaginable. Immortality without choice, life without end, experience without escape. Welcome to forever. You did not ask for this, you cannot refuse it, and it has only just begun. Chapter 10. What happens when you close your eyes? We began this investigation with a question. What if death is not an ending? Now, after 9 chapters of physics and philosophy, of mathematics and metaphysics, we must ask the question that matters most. What does this mean for you tonight when you close your eyes? The many worlds interpretation says that reality branches at every quantum measurement. Hugh Everett's math says the wave function never collapses. Max Tegmark's argument says that conscious experience can only continue in branches where the observer survives. Put these together, and you get quantum immortality. The claim that from your subjective point of view, you will never experience death. Is it true? Honestly, we do not know. The many worlds interpretation is one of several competing interpretations of quantum mechanics. It has passionate supporters and equally passionate critics. No experiment has separated it from Copenhagen or any other interpretation. The debate is about philosophy and mathematics, not direct measurement. Even if many worlds is true, the argument for quantum immortality makes assumptions that could be wrong. It assumes that consciousness is tied to specific physical processes that branch along with the wave function. It assumes there are always survival branches, no matter how unlikely. It assumes that subjective experience follows branch identity in a certain way. Any of these assumptions might fail, but here is what we do know. The universe is stranger than we ever imagined. Quantum mechanics has been confirmed with amazing precision. Particles really do exist in superposition. Measurements really do seem to collapse the wave function. The observer really does seem to have a special role, somehow, in some way we do not fully understand. Whether many worlds is the right explanation, some explanation is needed. And whatever that explanation ends up being, it will almost certainly be weirder than our everyday feelings about death and consciousness. So let us consider the possibilities. Possibility 1, the Copenhagen interpretation is correct. The wave function collapses when you measure it. There is only one universe, one history, one result for each quantum event. When you die, your consciousness ends completely and forever. There is no continuation in other branches because there are no other branches. Death is what it looks like, an ending. This is the common view, the one most physicists quietly assume in daily work. It is also the bleakest. If Copenhagen is true, then your experience has a real stopping point. One day, maybe decades from now, maybe tomorrow, you will close your eyes and never open them again. The lights go out, the story ends, and there is no observer left to notice. Possibility 2. Many worlds is correct, but quantum immortality fails for some reason. Maybe consciousness does not branch the way physical systems do. Maybe identity cannot continue across endlessly many branchings. Maybe there is a smallest unit of consciousness, a minimum base below which experience cannot happen, and eventually all survival branches drop below that threshold. Maybe death, even in many worlds, is truly final once the chance of meaningful survival becomes low enough. This view keeps the weirdness of many worlds without the terrifying results of quantum immortality. You exist in a branching multiverse. Other versions of you live other lives, but you in this branch will someday die, and that death will be final for you even if other versions continue. Possibility 3. Quantum immortality is real, and everything we explored in this investigation is correct. You will never experience death. You will always find yourself in a survival branch, no matter how unlikely. Your subjective experience will continue without end through suffering and chain, and the slow thinning of probability, until you live in branches so thin they look like miracles. This is the possibility that scares and fascinates at the same time. Immortality without choice, persistence without peace, a future that stretches forever because the dead versions cannot report their deaths. Possibility 4. Something else entirely is happening. Maybe consciousness is not physical at all. Maybe it exists in some deeper layer of reality we have not discovered. Maybe death is a transition, not an ending, a shift from one kind of experience to another. Maybe the mystics were right, and physics is only scratching the surface of what we are. This is the most speculative possibility, the one that goes beyond what science can currently answer. It offers hope or fear depending on who you are. It suggests that the question of what happens when you die might not have a physical answer at all. Which possibility is correct? We do not know, we may never know. The experiment that would decide the question, the first-person test of quantum immortality, is one that cannot be shared. If you die, you cannot report it. If you survive, others in your branch see you survive. But that proves nothing about the branches where you died. The truth may be hidden from us forever. We may live and die without ever knowing whether death is an ending or a fork in the road. But here is what I want to leave you with. The question matters. The uncertainty matters. The sheer strangeness of the universe we live in matters. For most of human history, people believed that reality was roughly what it looked like. Solid objects were solid. Time flowed evenly. The world had one history, one future, one truth. Death was the end of the story. Sad but understandable. A return to the nothing we came from. Quantum mechanics shattered this picture. Reality at the deepest level is nothing like everyday life. Particles are waves. Waves are particles. Possibilities stack on top of each other until observation forces a choice. And maybe, just maybe, all the possibilities are real. All the choices are made. And we are living in an infinite garden of forking paths where every road not taken is taken by someone who used to be us. If this is true, then death is not what we thought. It might be an ending in some branches and a continuation in others. It might be the moment when the crowd of selves that began as you finally shrinks to a single thread. Or it might be a transition that is not an ending at all, a passage through the narrowest part of the funnel and into something new. We do not know. We live inside the question. And that question, that beautiful and terrible uncertainty, is part of what makes being human so strange. We are creatures who can think about our own death, who can wonder whether death is even real, who can use math and logic to peek beyond the curtain and catch glimpses of structures too vast to understand. You will close your eyes tonight. Maybe you will open them in the morning. Maybe if many worlds is true, every possible version of tomorrow will happen. Maybe you will wake in a million branches and die in a million others. Maybe the you who wakes will remember reading this and wonder if any of it was true. I cannot tell you what will happen. I can only tell you that the question is real, that the physics is real, that the strangeness we explored is not made up, but the sharp edge of what we understand about the universe. Hugh Everett died in 1982. Or maybe he did not. Maybe somewhere in some thin branch of the wave function, he is still alive, still thinking, still working out the consequences of the theory he proposed as a young man in Princeton. The theory the world rejected, the theory that might be the truth about everything. He wanted to live forever, or at least he wanted to believe that death was not the end. His theory gave him that possibility, not as faith, not as wishful thinking, but as a logical result of the math he trusted more than anything. Maybe he was right. Maybe at this very moment, a 94-year-old Hugh Everett is sitting in a library somewhere, reading papers that cite his work, smiling at how far it has come. Maybe he has lived 1,000 lives in 1,000 branches, each one as real as the life he left behind. Or maybe he is simply gone. Maybe the wave function collapsed after all. Maybe death is death, final and complete. The end of the story with no sequel. We do not know, we cannot know. And in that not knowing and that deep uncertainty about the biggest question we can ask lies the strange beauty of being alive. You exist, you are conscious. You are reading these words in this moment, in this branch, in this thin slice of the possible. Whatever happens next, that is remarkable. That is enough. That is everything. Close your eyes, dream your dreams. And when you open them again, whether in this branch or another, remember that you are part of something vast and strange and barely understood. The multiverse may be endless. Your questions may never be answered, but you are here now asking them, and that might be the only immortality that matters. If you enjoyed this deep investigation into quantum mechanics and the nature of consciousness, please like this video and subscribe to the channel. Your support makes these explorations possible. Tell me in the comments, do you believe in quantum immortality? Does the many worlds interpretation comfort you or scare you? And what topic should we investigate next? The universe is full of mysteries. We've only scratched the surface. And as long as there are questions to ask, we will keep asking them. Thank you for watching. I will see you in the next investigation.